Welcome again to to a new lecture of solar photovoltaics principles, technologies and materials. So, from today we will start discussing from this lecture onwards we will start discussing the technologies that are present in solar cell landscape. So, we will just have a little recap of the last lecture. So, the recap of the last lecture is that we learnt about solar cell device parameters. So, we saw what is short circuit current, what is open circuit voltage, what is fill factor and what is efficiency, and we also saw that a typical IV curve of a solar cell device is like this. It is in the fourth quadrant. So, the current at 0 voltage is short circuit current, the voltage at which current is 0 is open circuit voltage, and within this curve there is a rectangle that you can draw which corresponds to maximum power point, and this basically comes from D of JV into V. So, wherever this is equal to 0, that is the maximum power point. Corresponding to this maximum power point, you have IM, which is the maximum current that can be extracted, and VM, the maximum voltage that can be extracted. So, this is the maximum power that you can draw out of a solar cell, which is within the IV curve, experimental IV curve. So, the idea of engineering, materials and device engineering is that your aim is to make this curve as square or as rectangular as possible, which means that series and shunt resistance must be optimized. If you have a bad solar cell would appear like this. So, if you now want to draw the MPP in this, the MPP would correspond to something like this. Okay. So, for a bad solar cell, the fill factor is lower than that of a good solar cell, right. You can see that the fill factor of this red rectangle is the area of this red rectangle is bigger than the area of smaller rectangle, and this is for the same VOC and ISC approximately, and this is manifested in fill factor. So, you can see that for the black curve, the series resistance is so for the black one, the different color now, for the black one the series resistance is nearly equal to 0, whereas the shunt resistance is nearly equal to infinity. So, basically very large, okay, and this is very small. And for the blue one, you can see that the series resistance is RS is large, and for this RSH is smaller, and this is what results in. So, fill factor is basically, as we said, is given as VM IM divided by P in. This is the incident power, and this is the incident, you can write in terms of energy or power. So, let us say this is VM IM, which is the incident, which is the extracted energy out of a solar cell, and this is the incident energy. So, if VM IM goes down, this is efficiency, yeah, so and this is equal to fill factor into VOC into ISC, right, PN, yes, you are right, this should be efficiency. So, the ratio of VM IM to the incident power gives you the efficiency, and this is related to fill factor. So, VM IM is equal to fill factor into VOC into ISC. So, if your fill factor is higher, your efficiency of power extraction is going to be, power conversion is going to be better, which is where you write fill factor as VM IM divided by VOC into ISC. Okay. So, idea, so you can see from these expressions, you want to maximize VM IM, which is by maximizing VOC fill factor, but you also would like to maximize VOC and ISC. So, for a device engineering perspective, fill factor depends upon the quality of device, quality of junction and device. Basically, the job is to minimize the parasitic resistances. VOC, as we saw last time, depends upon the band gap. So, your larger the band gap is, larger the VOC is going to be, but if you increase the VOC, your current also drop. When you increase the band gap, the current drops. So, both ISC and VOC to some extent are determined by EG, and there is an optimum EG that you need to use. So, but it depends upon the materials which are available to you. So, typically we will see that the range varies from anywhere from 1 electron volt to 1.7, 1.8 electron volt, and within this we get whatever VOC and GSC we have. And but VOC and GSC are also dependent upon the recombination in the devices. So, if your device is bad, if your material quality is bad, then even though material has promised to give you higher VOC and GSC, you will end up with a lower VOC and GSC because the material quality is bad. So, all of these factors are quite intertwined with each other, they are interrelated to each other, and many of the times for a given material they are dependent upon the kind of quality that you get after the thin film or device fabrication process. So, next I would just again draw the curve between the, as we saw last time. So, this is the efficiency curve with, as a function of EG, and this curve goes something like this, and this maximum efficiency is about 33%, and this falls around the band gap of nearly 1.4 EV. So, we have somewhere here about 30, we have gallium arsenide. So, this is gallium arsenide. So, this is thin film gallium arsenide, this is bulk gallium arsenide. Silicon is somewhere here, its band gap is 1.1. So, this is silicon, this is at about 24% or 24.7%. Polysilicon is lower, this is polysilicon, which is at about 17-18%. Then we have CIGS, which is CIGS, which is again at about 18-19%, and then we have CDTE also somewhere here, which is about 19% or so. These are approximate numbers, and then we have perovskite, which has already approached 20%. So, perovskite would be somewhere here, perovskite. Organics are lower, around 13-14%, although there are reports of 15% nowadays. So, you can see that these are different materials that you have in different domains. So, band gaps are centered around 1.5 electron volt. Some materials have band gaps higher than 1.5 electron volt, some materials have so materials like silicon, CIGS, they have lower band gap. Okay. And their efficiencies are of the order of so silicon is crystalline silicon is about 24%, CIGS is about 19%, CDT band gap is larger. So, around 1.4 EV, this is silicon is about 1.1 EV, this is about 1 EV or so, it depends upon the composition. CDT again gives you about 19%, gallium arsenide is 1.4 or so, this gives you about nearly 28% or so, 28 to 30% roughly, and crystalline. So, you have various numbers for gallium arsenide. Perovskites have a band gap which is higher than so higher band gap, so greater than 1.5 EV, and they give you eta today, as of today, about 23%. These are efficiencies at the cell level, not at the module level. Okay. So, laboratory scale efficiencies. Organics give you more than 1.5 eV, again they give you efficiency of the order of 15% or so. And on top of these we have tandem cells where we can mix and match the band gaps. As I said last time, you can stack them together, they give you higher efficiencies. So, but in this course mostly we will be talking about the single junction devices, not the multi junction devices. So, there is in the solar cell literature jargon, there is another term that will come into consideration, is called as quantum efficiency. Quantum efficiency is essentially the probability of conversion of a photon into electron hole, an electron, or you can say electron hole pair, okay, or a EH pair which eventually gets separated and gives you electron and a hole. So, it depends upon various factors. So, the first factor it depends upon is reflection, and efficiency of reflection is depicted as eta O. It also depends upon absorption and electron pair or exciton formation. Efficiency of that is eta A, that is absorption and formation, okay. Exciton dissociation, once the exciton forms it has to dissociate, and there is exciton dissociation efficiency corresponding to that, that is eta ED. And then charge separation and transport, that is eta CT, and then efficiency of charge collection at the electrodes, which is eta CC. So, the net external quantum efficiency is a product of all these efficiencies: the optical efficiency, the reflection one, the absorption and exciton formation efficiency, that is eta A, exciton dissociation efficiency, which is eta ED, charge separation and transport, which is eta CT, and eta CC is the charge collection. So, you can see each of these factor is an independent factor determined by various factors. So, eta O is going to be determined by the reflectivity of the top surface, okay, and that is why in the solar cells we use nowadays anti-reflection coatings, especially for silicon and other kind of solar cells, not so much for organics and perovskites. So, basically you would like to minimize the reflection losses, which means you would like to make this eta O close to 1. Then we have eta A, which is absorption. So, basically above the band gap all the energies must be absorbed. So, you want to maximize this absorption efficiency. So, this is related to alpha A and the band gap. And then we have, so above the band gap basically you would like to absorb everything. Then we have exciton dissociation. This is usually not a problem in case of inorganic semiconductors, but could be an issue in organic semiconductors. So, this is a problem in organics. Otherwise, it is all right, you get pretty high exciton dissociation efficiency in inorganic semiconductors. Absorption efficiency of course is higher for direct band gap semiconductors than for indirect band gap semiconductor. And then we have charge transport. Charge transport depends upon the type of semiconductor you have, what is the series resistance you have, do you have any losses within during the transport. So, that will be determined by material and device quality, okay. The parasitic resistances and so on and so forth. And then you have efficiency of charge collection, what kind of electrodes you have on the surface, what kind of, are there any traps at the electrode interface, whether they have the right work function to extract the charges. So, this is determined by the electrodes. So, you can see that your device design will require to optimize all of these. You would like to minimize reflection, you would like to maximize the absorption, you would like to maximize the efficiency of exciton dissociation, which is normally not a problem, but you must have some built-in field or built-in force to break the exciton and dissociate into electron hole pairs, especially in organics. Then we have charge transport, which is you need to maximize the charge transport efficiency, so that charges are not lost or impeded on the way, which is determined by material and device quality. And then we have electrodes which come into picture, because the kind of energy levels, the kind of conductivity of electrodes, the kind of interfaces they make with the solar cells is very important in charge collection. So, all of these together will give you external quantum efficiency, which is called as eta EQE, and this can be experimentally measured, okay, and this can be directly correlated to the current, okay. So, ideally the current that you obtain should scale with the external quantum efficiency, all right. So, if you look at a PV device based on this efficiency, there are the operations are fairly straightforward. So, the operations in a PV device is, first you have light absorption, then you have creation of exciton, then you have exciton dissociation, then you have diffusion to the electrodes, and then you have charge collection. And this is what the as we saw, the external quantum efficiency is made up of. So, if you, for example, if you look for a given device, let us say we have a photon flux density as a function of wavelength. So, photon flux density goes as something like, it goes as something like that, right, and it goes to higher wavelengths. So, this is your photon, and these are absorption bands at different wavelengths. And so, the quantum efficiency, let us say you have a solar cell whose band gap is somewhere here. So, if this is the solar spectrum that is reaching the solar cell, the quantum efficiency 100% would mean that you will absorb everything, you will not lose everything, and as far as the solar cell permits, right, it will not absorb anything below the band gap. So, starting from here up to the band gap, it will absorb everything. So, this would mean that your quantum efficiency is equal to 100% because you have absorbed everything that was available to you, and which has led to formation of electron and hole pair. So, essentially 100% QE would mean that 100% conversion of photons into electron hole pairs which get collected. So, there are no losses, right. So, there are no losses. That is the objective we have, and this depends upon various factors as we just saw. So, now let us look at the more practical aspects of solar cell devices, that is the evolution of solar PV first before we go to Gen 1. So, evolution of solar PV has happened through stages. So, 1839 was the time when Becquerel discovered this light electricity conversion, which was called as photovoltaic effect. He was a French physicist, and this was determined from experiment using metal electrodes and using electrolyte whose conductance changes with the illumination. So, this was in 1839. The first solar cells, however, were made in 1873 when photovoltaic effect was discovered in selenium, and then 1877 was the time when first selenium solar cell was made. Of course, there are a lot of other intermediate stages which which we do not have time to get into, and then came the age of silicon. So, 1918 first, after the First World War, we have Shklovsky who discovered a method for making monocrystalline silicon. However, the first silicon monocrystalline solar cell came in 1941. And then in between in 1932 people also observed PV effect in cadmium selenide. And then we have 50s to 60s when intensive space research was conducted primarily on solar. So, because the problem with the space was if you wanted to sell satellites, you needed them to be powered up, right, and you couldn't, there is no way you can send cables from Earth to space. So, what was the source of electricity? The photovoltaics was the source of electricity. So, photovoltaics benefited from satellite the space programs of US and Russia at those times, and cost was not a factor. So, as a result, intensive effort was made to develop solar cells of high efficiency because you wanted to reduce the weight of satellite. If you had lower efficiency solar cells, which means you need to put in more solar cells, which will increase the weight of the satellite. So, there was a lot of effort on making high efficiency solar cells so that satellite could remain powered up in the space. So, 1951 the first germanium solar cells were made, 1954 cadmium sulfide solar cells were made with 4.5% efficiency, which was increased to 6% in a few months. And then in 1957 we had solar powered cars, and 1950s we have solar powered cars and satellites. So, 1958 was the time when first radiation proof, radiation is a problem in space. So, as a result radiation proof silicon solar cell was needed. It was made in 1958, then March 1958 the first satellite powered by solar cells, that is Vanguard 1, was launched in the United States. And then 1959 and 60s led a phenomenal increase in the efficiency of silicon solar cells. It went up to 14%. 1955 was the time when we had first sun powered automobile in Chicago, and this paved the way for solar module development, that is large scale solar power development. 60s and 70s there was a massive effort on developing solar modules. 1980s lot of large standalone photovoltaic systems were developed, not necessarily grid connected and for commercial purposes. 80s there was an effort on solar cars also, and then 80s also we started research on thin film technologies, and these were important because silicon solar cells were heavy, because they use wafer of silicon cells. So the idea was to reduce the weight of the solar cell and reduce the material cost also by using materials in thin film form. So there was a lot of effort on developing technologies which were thin film technologies, such as cadmium telluride, CIGS, amorphous silicon, and so on and so forth. And then with the discovery of new materials, 1990s Gratzel's group discovered the dye sensitized, that is electrochemical solar cell. 2000s a lot of research was done on organic solar cells, which is based on polymer and plastics based materials. And in 2010 we have intensive research on perovskite solar cells, and somewhere in between we also have multi-junction solar cells. Multi-junction solar cells, the work started quite early because of ability to match the band gaps, and people saw potential in increasing the efficiency, although they are expensive. So this is sort of a chronological development of solar cells over the years, and because of this the solar cells are often characterized in three categories. First is the Gen 1 PV. Gen 1 PV is primarily based on silicon and gallium arsenide, which started in 1960s or 50s. Okay. So then we have Gen 2 PV. This is basically on thin film and multi-junction solar cells, and this is primarily based on cadmium telluride, copper indium gallium selenide, SIGS as we call it, amorphous silicon, and so on and so forth. And so this is Gen 1, this is Gen 2, and then we had if I now draw a line here, and then we have Gen 3, which means dye sensitized, organics, and perovskites. So these are the three categories of solar cells which have been in which we can divide the journey of solar photovoltaics. Okay. And this is how we will go. We will first look at some of the aspects of Gen 1 solar cells and material issues, technology issues, design issues. Then we will move on to Gen 2 PV, which is mainly thin film silicon, thin film solar cells and multi-junction solar cells. And finally, we will look at the issues and materials related to the dye sensitized perovskites and organic solar cells. Okay. So this is the order in which we will go now in this course. If you want to go through books, I would suggest this for silicon and thin film technologies, at least Gen 1 and Gen 2. This handbook is very good. This is Handbook of Photovoltaic Science and Technology by Antonio Luke and Stephen Hegedus from Wiley. Excellent book for Gen 1 and Gen 2. Again, we have another book, nice book by KL Chopra and SR Das, Thin Film Solar Cells. For organic and perovskites, there are not many books available, but for organic photovoltaics, you can go through this book on organic photovoltaics concepts and realization by Brabeck, Diakonov, Parisi, and Sarifepsi. For perovskites, there are several review articles in journals. Okay. And similarly for DSSC, that is dye sensitized solar cells, there are books, edited books as well as review articles. Okay. However, for all of them you will also find a lot of review articles, very nice review articles written on each of the technology, solar cell technology. And of course, you can look at this book, Physics of Solar Cells, by Jenny Nelson. It does not talk so much about the manufacturing, it is mostly about the science of solar cells. Alright, so as I said, first generation technologies are 1950s, the work started. So they were primarily based on single crystalline silicon and gallium arsenide, and also the work started on multicrystalline silicon during this time. They are of high cost but high efficiency, okay, and this is a high efficiency was a reason why a lot of efforts were made on these technologies, because they could reduce the weight of satellites and weight of panels in general for other applications as well. Then the second generation work started in 70s and 80s. So we have thin film technologies mainly, and this could be amorphous silicon, primarily amorphous silicon, CIGS and CDTE, but also multi-junction solar cells. And third generation 2000s, we have work on organic solar cells, dye sensitized solar cells, where work started in 1990s, although perovskite solar cells, and we also have tandem solar cells, okay. Multi-junction will also fit in this category. The work on multi-junction started actually quite early, okay, multi-junction or tandem solar cells, okay. And this is a famous efficiency plot from NREL, which publishes this in the public domain, and this diagram is referred by most of the researchers out in the world. And you can see that if I go for first the crystalline silicon is in the blue lines, and the non-concentrator technology silicon is about 25.8% as of 2000. So this one on the right here. So this is the one which is this one, okay, 25.8. And if you use the concentrator technology, which uses the concentrated sunlight, the efficiency is about 27.6%, which means the intensity is not AM 1.5, it is higher than AM 1.5. And if you go to thin film technologies, the ones in the green, the CIGS has a number of about 23% right now, laboratory scale. So it's in the concentrator mode. If you go to non-concentrator mode, the efficiency is about 22.6%, which is here. This is non-concentrator. And cadmium telluride is about 22.1%. These are laboratory best efficiencies, okay. But these are not the average efficiencies. So these are the world records in that sense. And then amorphous silicon lies low at 14%, and the work on amorphous silicon is almost stopped now. And the emerging PV is the one which is the third gen technologies, and that is where we have perovskite leading the chart at 22.7. Right now it is more than 23% as we speak today, the world record. And then we have organics. So the one, this is quantum dot at 13.4. Then we have inorganic CZT, which is copper zinc tin selenide, which is again a new PV technology, about 12.6%, a very promising one. Then we have organics in the red dots, which is at 11.5. Right now it is about 13-14% the world record. So there are various technologies, and you can see on top of the chart we have these multi-junction technologies, which include more than one material, okay. So for example, right on the top we have this 4-junction technology, which is at about 46%, but these are very expensive technologies and very difficult to make. So they are primarily for demonstration purposes or solar or space technology programs, or for some niche applications. And mostly the research on these is led by industries. You can see that the research is mostly industrial centers or groups led. Then we have 44.4%, which is in triple junction concentrator. So this is for triple junction. And then we have various other concentrator technologies, as you can see on the left here. So you can see here in the summary, the concentrator technology leads the efficiency chart right now, which the multi-junction technology, which uses more than one junction. And then we have silicon, perovskite, and then we have thin film PVs, and then we have a lot of other emerging PVs. So future is quite bright as far as solar energy is concerned, and given that recently we have had cost reductions in silicon photovoltaics, the future is certainly quite bright. So, right now as of 2014 report, the technology share, multi-silicon has a technology share of about 54.9%, and in case of silicon you can see the numbers here. Multi-crystalline silicon is this, the blue square, and multi-crystalline stands at about 22%, which is not bad, and because considering that cost of multi-crystalline silicon is lower than single crystal silicon. So, multi-crystalline leads the way because of lower cost as compared to single crystal silicon with about 55% market share. Mono silicon, which is crystalline single crystal silicon, is about 36%. So, together they have a market of nearly 90%, and remaining 10% is occupied by cadmium telluride, amorphous silicon 2%, CIGS 2%. Amorphous silicon is now pretty much a closed technology. There are not too many investments coming up in this technology, and it is expected that cadmium telluride and CIGS share will rise as a function of time. It is also possible in the future perovskite and some other technologies start entering the market. Perovskite and other technologies are still on the research stage, they have not been commercialized, but it is likely because the lifetimes are an issue, but once the lifetime issues are solved, there is a possibility that they might enter into the market. So, one of the key attribute of a solar cell technology is that since solar cell technology is not very cheap technology as of now, the lifetime is a major issue. So, one would expect a solar panel which is installed in a solar farm in your house to at least last for 20 years. So, there is this 20-year requirement, that is a very stringent requirement on the new technologies, and that is why most of the technologies are not able to beat inorganic solar cells when it comes to lifetime. So, let us come to the principle of cell design. So, how do you design the cell in a solar cell? So, the first thing is, as we said, from the quantum efficiency perspective, the optical depth of the device, that is alpha E absorption coefficient into Wp plus Wn, which is the width of depletion region total, should be high for energies above Eg. So, which means the optical depth, the depth in which solar cell absorbs, the device absorbs light, that should be good enough so that you are able to absorb all the energies above Eg. The device must have low reflectivity, it must have large built-in field for effective charge separation. Okay. The junction should be close to the surface, so that you have so we will come to the reasons for this, especially in case of silicon it is very important. The junction should be close to the surface, and this is mainly because of recombination in the different types of materials. The device must have a small series and large shunt resistance, as we have seen. The minority carriers must have long lifetimes and diffusion lengths with a small surface recombination velocities. The material must have optimum band gap, and generally we prefer, especially for silicon, a heavily doped emitter, that is on top, and a lightly doped base, and this is mainly to ensure you have good contacts and vector collection in especially in the base region. So, we will come to the details of these from the perspective of silicon in the next lecture, because we are running out of time for this lecture. And so, what we have discussed is basically the evolution of solar cells and general framework, in which we will now discuss the rest of the lectures. Thank you.